On the 22nd of June, 2026, a research team working out of NASA's Goddard Space Flight Center published a paper in the journal Nature that quietly rewrote what we thought we knew about the object called 3I Atlas. No press conference, no dramatic unveiling, just a peer-reviewed document dense with numbers that confirmed something almost too strange to say out loud. The comet passing through our solar system right now is older than the Sun itself, older than Earth, older, in fact, than most of the stars you can see in the night sky. And the instrument that proved it was the most powerful telescope humanity has ever built, pointed at a fragment of ice and rock that has been drifting through the galaxy for roughly 12 billion years, waiting, in a sense, for us to notice it. To understand why this matters, you have to go back to the 1st of July, 2025, when the Atlas survey telescope in Chile caught a faint smear of light moving in a way nothing in our solar system moves. Astronomers ran the numbers, and the trajectory did not make sense for anything native to our sun's gravity. The object was moving on a hyperbolic path, too fast to be captured, too fast to ever return. It was not orbiting the sun. It was passing through the way a stranger passes through a town on a road that leads somewhere else entirely. Within days, the object was confirmed as only the third interstellar visitor ever detected in human history, after C. Oumuamua in 2017 and 2I Borisov in 2019. It was given a name, 3I Atlas. And almost immediately the questions began. Where had it come from? How long had it been traveling? And what exactly was it made of? For months, telescopes around the world tracked it as it fell inward toward the sun, reaching its closest approach, its perihelion, on the 29th of October, 2025, at a distance of about 203 million kilometers, tucked between the orbits of Earth and Mars. It never came anywhere close to threatening our planet. The closest it ever got to Earth was roughly 270 million kilometers away. This was never a story about danger. It was a story about origin. And origin stories, as it turns out, are written in chemistry. As 3I Atlas approached the sun, its surface began to warm just slightly, just enough for the frozen material locked inside it for billions of years to start turning directly from solid to gas. Astronomers call this outgassing. It is the same process that gives any comet its glowing halo in its tail, the release of ancient ice transforming into vapor and streaming outward into space. But it is also something else. It is a window. Because the gas escaping from a comet carries with it the exact chemical fingerprint of the environment where that comet was born, every molecule released into that glowing coma is a message, sealed for eons, finally breaking open. This is where the James Webb Space Telescope enters the story. In December of 2025, as 3I Atlas was receding from the sun and approaching the region where water ice stops readily turning to vapor, a team led by researcher Martin Cordner pointed Webb's near-infrared spectrograph directly at the comet. NIRSpec does not take a photograph in the way people usually imagine a telescope working. It splits the light coming from an object into its component wavelengths, the way a prism splits sunlight into a rainbow, and in doing so, it reveals the unique spectral signature of every molecule present: carbon monoxide, carbon dioxide, water, methanol, methane. Each one leaves its own signature in the light, and Webb read every single one of them. What it found should not have been possible for an object this size, moving this fast, this far from any star. The first anomaly involved methane. Webb detected a methane-to-water ratio roughly 11 times higher than anything ever measured in a solar system comet. 11 times, not a marginal deviation, not something you could explain away as measurement noise, an overwhelming excess of methane relative to water, a ratio so far outside the normal range that it forced researchers to reconsider what kind of environment could have produced it in the first place. Somewhere, in the cold dark of interstellar space, something was baking methane into this object at a scale nothing in our own solar system has ever replicated. But the methane was only the beginning. Webb's spectrograph also measured the ratio of deuterium to ordinary hydrogen inside the comet's ice. Deuterium is a heavier isotope of hydrogen, carrying an extra neutron in its nucleus, and the ratio between deuterium and regular hydrogen in any icy body is essentially a temperature record, a frozen thermometer reading from the moment that ice first formed. The colder the environment, the more deuterium tends to get locked into the ice. When the Webb team measured this ratio, in 3I Atlas, they found it sitting at roughly 0.98%. Comets born in our own solar system typically show deuterium ratios many times lower than this. NASA and the European Space Agency both confirmed the number independently. The ratio measured in 3I Atlas was approximately 30 times higher than what is typical for a solar system comet. 30 times. Sit with that number for a moment, because it is not a small technical footnote. A deuterium enrichment at that level points to an object that formed in one of the coldest environments physics allows for solid ice to exist, somewhere near 30 degrees above absolute zero, roughly minus 200, and 43 degrees Celsius. That is not a temperature you find inside a young, forming solar system close to a warming star. That is a temperature you find in the deep, undisturbed cold of a molecular cloud, far from any stellar furnace, in the kind of environment where matter can sit frozen and essentially unchanged for unimaginable stretches of time. And then came the detail that turned a strange discovery into a genuinely historic one. Every time a new generation of stars is born and dies inside a galaxy, it seeds the surrounding gas with slightly heavier isotopes of carbon, specifically carbon-13, through the nuclear furnaces inside stellar interiors and the explosive deaths of massive stars. Over billions of years, generation after generation, the ambient level of carbon-13, relative to ordinary carbon-12 in the galaxy, gradually rises. It is a slow, steady enrichment, a kind of cosmic clock ticking forward with every stellar life cycle. When researchers examined the carbon isotope signature inside 3I Atlas, they found something almost eerie. Trace minimal levels of carbon-13, levels so low they matched what the galaxy would have looked like before generations of stars had time to enrich it. The implication was staggering. Based on this isotopic signature, researchers calculated that 3I Atlas likely formed somewhere between 10 and 12 billion years ago. For context, our own sun and solar system are approximately 4.6 billion years old. This means the object currently drifting through our sky, visible even now to telescopes on Earth, condensed out of a cloud of gas and dust before our sun existed. Before Earth existed. Before most of the stars currently burning in our galaxy had even ignited. It formed during what astronomers call the peak era of star formation in the universe's history, a period when galaxies were producing new stars at a rate far higher than they do today. This was not a young comet that happened to travel a long way. This was possibly one of the oldest solid objects that has ever been directly observed and chemically analyzed by human instruments. If this had come from a single team, a single paper, a single data set, it would already be remarkable. But science does not run on a single confirmation. And this is where the story gets even more solid. In early July of 2026, an independent team led by Cyril Optom of the University of Edinburgh, using the European Southern Observatory's Very Large Telescope in Chile, published their own analysis in the same journal, Nature Astronomy. Using a completely different instrument, looking at different molecules, including cyanide compounds built from carbon and nitrogen, the VLT team arrived at strikingly similar conclusions. They found that 3I Atlas carried far more carbon-12 relative to carbon-13 than typical comets, reinforcing the idea that it formed when the wider galaxy was still isotopically young. They also found that its nitrogen ratios closely matched what scientists observe at the cold outer edges of planet-forming disks, similar in some ways to conditions found at the far reaches of our own Kuiper Belt, but transplanted from an entirely different star system, billions of years in the past. Two separate teams, two separate telescopes, two separate sets of instruments, operating independently on different continents, converged on the same extraordinary conclusion. That is not how flukes behave. That is how confirmed science behaves. There's a very natural question that comes next. And if you have been paying attention to interstellar object coverage over the past year, you already know it is coming. If something this old, this strange, this chemically unlike anything in our solar system shows up moving on a hyperbolic trajectory through our sky, could it be something other than a comet? Scientists took that question seriously because ignoring it would have been bad science. A comprehensive search for artificial radio signals, a SETI-style techno-signature search, was conducted on 3I Atlas. It found nothing. No transmissions, no anomalous radio emissions, no signature inconsistent with natural physical processes. Every single observed behavior of this object, the outgassing, the coma, the chemical composition, the trajectory, is fully explained by ordinary comet physics, acting on an extraordinarily old and extraordinarily well-preserved piece of primordial ice. NASA and the broader scientific community are unambiguous on this point. 3I Atlas is a natural object. What makes it remarkable is not what it might be hiding, but exactly what it is. A physical time capsule from a period of the universe's history that we have never before been able to touch, sample, or measure directly. Think about what that actually means for a moment. Every telescope humanity has ever pointed at deep space, from Hubble to Webb to the largest ground-based observatories on Earth, has only ever been able to look at light. Light that traveled across unimaginable distances, arriving billions of years old, showing us galaxies and stars as they existed in the ancient past, but always at a remove, always as photons, never as physical material. We could directly study. 3I Atlas is different. It is not a photograph of the ancient universe, it is a piece of it. Actual matter, actual ice, actual frozen chemistry, formed 10 to 12 billion years ago around a star system we will likely never identify, now passing directly through our solar system, where our most advanced instruments can sample its composition molecule by molecule. We are not looking at the deep past. For the first time, in a very real sense, we are touching it. And there is something almost poetic about the timing of its warming near the sun. For 10 billion years or more, this object drifted through the near absolute cold of interstellar space, its chemistry locked, frozen, unchanged, an untouched fossil of a galaxy that no longer looks anything like it did when this ice first formed. Then, by pure chance, its long, silent trajectory intersected briefly with our own small corner of the galaxy, just close enough to our sun's warmth to begin releasing the very gases that would let us read its history. Had its path been even slightly different, had it passed by a few million kilometers further out, it might never have generated a coma bright enough for Webb, or the VLT, or any Earth-based instrument to study in this kind of detail. Instead, it happened to pass close enough, at exactly the moment in human history when we possess a telescope capable of decoding it. The object is now moving away from the sun, following the same hyperbolic path that brought it in, accelerating back out into the depths of interstellar space. It will never return. Whatever star system it originally formed around, whatever world or debris disk once surrounded it 10 or 12 billion years ago, is almost certainly gone now, transformed or destroyed by the same billions of years of galactic evolution that eventually gave rise to our own sun and our own Earth. 3I Atlas carries no message, no intention, no destination. It is simply an ancient wanderer, continuing a journey that began before most of the galaxy's current stars had even been born, a journey that will now continue, indifferent and unbroken, long after every telescope currently tracking it has gone silent. What the Webb data actually gives us, more than anything else, is a kind of chemical time machine, a way to reconstruct the conditions of star formation from an era of the universe we have never been able to sample directly before. The unusually high methane, the extreme deuterium enrichment, the near absence of carbon-13, together they sketch a picture of a cold, ancient, densely packed molecular cloud, forming solid material during the peak star-forming epoch of the universe's history, a period some astronomers call cosmic noon. Every model we build of how planetary systems form, how organic molecules assemble, how the raw ingredients for potential life get distributed across a galaxy, can now be tested against a real physical sample from that era, rather than theoretical extrapolation alone. There are still open questions the data has not answered. Researchers do not know, and may never know, precisely which star system 3I Atlas originally formed around. After 10 to 12 billion years and untold thousands of gravitational encounters with other stars during its journey across the galaxy, any trace of its original stellar neighborhood has almost certainly been erased beyond recovery. Nor do scientists know how many more objects like this one might already be drifting through the outer edges of our solar system undetected, waiting for a survey telescope somewhere on Earth to notice a faint, fast-moving smear of light on a night no different from any other. To appreciate how far the science has come, it helps to remember what happened the last two times an interstellar object entered our solar system. Oumuamua, discovered in 2017, came and went so quickly that by the time astronomers realized what they were looking at, it was already too faint and too distant for detailed spectroscopy. It left behind more questions than answers, an elongated, tumbling object with no visible coma, no clear cometary activity, and a strange, unexplained acceleration as it departed that some researchers still argue about today. Borisov, in 2019, behaved more like a conventional comet and gave astronomers a better look, but it too moved through our sky before the most powerful instruments available today had come fully online. Neither object could be sampled with anything close to the precision Webb now offers. 3I Atlas is the first interstellar visitor we have ever caught at exactly the right distance, at exactly the right moment in its outgassing cycle, with exactly the right telescope already sitting in space and ready to look. The timing matters more than it might first appear. Webb was not built with interstellar comets in mind. It was designed primarily to study the earliest galaxies in the universe, to peer back toward the aftermath of the Big Bang, to examine the atmospheres of planets orbiting distant stars. That an instrument built for one kind of ancient light would end up perfectly suited to reading ancient ice drifting through our own solar system is one of those quiet coincidences of scientific history that only becomes obvious in hindsight. The same infrared sensitivity that lets Webb detect the faint glow of galaxies from the dawn of the universe is exactly what let it resolve individual molecular signatures inside a comet barely a kilometer across, moving at tens of kilometers per second, hundreds of millions of kilometers away. It is worth pausing on the physical scale of what was actually measured. The nucleus of 3I Atlas is estimated to be somewhere between half a kilometer and a few kilometers across, depending on which observation is used, a body small enough that if you set it down in a mid-sized city, it would barely cover a handful of neighborhoods. And yet the coma of gas and dust it generated as it warmed near the sun swelled outward to nearly 700,000 kilometers across, far larger than the planet Jupiter, a glowing envelope of ancient vapor visible to telescopes across the solar system. all sourced from a solid core smaller than most towns. That contrast, an object you could walk across in an afternoon, producing a cloud of gas large enough to swallow worlds, is part of what made this particular flyby such a rare opportunity. There was simply more material outgassing, more signal for Webb's instruments to capture, than either of the two interstellar objects that came before it. The molecular mapping itself, published as part of the coma physics survey conducted in December of 2025, tracked 5 separate volatile compounds simultaneously: carbon monoxide, carbon dioxide, water, methanol, and methane, across the full extent of the coma, essentially building a 3-dimensional chemical portrait of the gas cloud as it expanded outward from the nucleus. Researchers were able to watch how the balance between these molecules shifted as 3I Atlas moved further from the sun and cooled, crossing into the region roughly 2 to 3 astronomical units out, known as the water ice line, where water stops actively sublimating and the more volatile compounds like carbon monoxide and carbon dioxide begin to dominate the comet's activity instead. That transition, captured directly by Webb, offered scientists something they rarely get: a live, evolving readout of a comet's internal chemistry changing in near real time. None of this happened without scrutiny. Every unusual number to come out of the 3I Atlas observations, the methane excess, the deuterium enrichment, the carbon isotope ratios, was checked, rechecked, and independently modeled before publication. Extraordinary claims about an object's age and origin do not get published in a journal like Nature on the strength of a single reading. The Goddard team's methane and deuterium measurements went through peer review. The Edinburgh team's carbon and nitrogen measurements, gathered independently using an entirely different telescope on the ground, went through their own separate peer review process. When 2 independently reviewed studies, using different instruments and different research groups, arrive at compatible conclusions about an object's age and formation environment, that is about as close to scientific certainty as a single passing comet is ever likely to get. It is also worth being honest about what this discovery does not do. It does not prove there is other life in the galaxy. It does not reveal the identity of the star system 3I Atlas came from. It does not change the object's trajectory or its complete lack of danger to Earth. What it does is far quieter and in some ways more permanent. It gives scientists a real physical anchor point for models of the early universe's chemistry, a way to test theories about how organic molecules, methane, water, and carbon compounds first assembled in the cold clouds where stars are born, using an actual sample rather than pure extrapolation from starlight alone. Every future model of early galactic chemistry will now have to account for what Webb measured in this one small ancient object. As 3I's our Atlas continues its outward journey, fading slowly from view as it crosses back beyond the orbit of Jupiter and eventually leaves the solar system for good, ground and space-based telescopes are expected to keep tracking it for as long as its coma remains bright enough to observe. Every additional week of data adds more resolution to the picture, more confidence to the isotope ratios, more detail to the map of a chemical inheritance carried across roughly a third of the current age of the universe. Somewhere in that data, scientists suspect, there may be still more to learn: subtler signatures, additional trace compounds, details that a first pass of analysis, rushed out under the pressure of a closing observation window, may not have fully captured. 2 more large interstellar objects have already been confirmed in less than a decade, after decades of searching for the first one. If that pace continues, it raises a quiet, almost unsettling possibility that these ancient visitors from other star systems are not rare at all, that our galaxy has been sending fragments of its earliest star-forming eras drifting past us all along, and we simply lacked the instruments until now to notice them, let alone read what they were carrying. Webb changed that. What it finds next, and what the next interstellar object turns out to be made of, remains, for now, entirely unknown.